Okay, today we are going to start with the last big topic that we're going to be learning about. If you'll download the notes from 42, the DISC method. Area, all of you that have finished the area test, I've got those, I think. I haven't graded any of them yet. I think Jasmine's taking hers tomorrow. So hopefully I'll get them back to you the first of the week on that. This requires lots of thought. This requires lots of ability to think and to visualize things in order to get a good hold of this. So I would ask you to pay attention and don't be afraid to ask a question. Typically, students sit here and do the head nod, and they don't have a clue what I'm talking about, but they sit there and nod their head like, yeah, I got that. I understand that, okay? Some students get this relatively easy if they can visualize things well. But we're going to spend several days talking about this to try and get you a good handle on it. If you would, look on your iPad and see if you have an app called A Little Calculus. I'm trying to show it on the screen up here so you can actually see what it looks like. But I'm not having any luck with that. My day is not going well. Okay, A Little Calculus. If you don't have it, we need to see about getting it for you. Ford, did you say you had it?
I don't.
Okay. Okay.
Yeah,
oh, yes, yes, it is. It's a red symbol-y thing like that's what you're looking for, okay? If you've got that, that's going to be good. This black background with a red funky-looking thing there. That's going to be very beneficial for you in a little bit to try and visualize what's going on here. So I want to start off with just a review, an easy review. There's the first equation I got for you. I want you to find the area between the curve, the x-axis, and the line x equals 1. Now, where are we talking about there? What region are we talking about? Here's the curve, y equals x squared. The x-axis, right here. And the line x equals 1 is right there. So we're talking about this region right here. What would be the integral that we set up to solve that problem? Who can tell us? Top minus bottom, which is what? X squared minus 0, so we'll just write it as x squared. And what are our limits of integration? 0 to 1. So we're starting right here. We're going all the way to right here. And remember, we talked about just kind of quickly that there's something called an accumulation function. Do y'all remember hearing and talking about the accumulation function? What do we mean by accumulation function?
it's like continually building.
That's right. It's just continually building. So I want you to think about this for a second now in terms of, think of it as an accumulation function here. We're going to just take small little snippets of this, and we're just going to continuously add them up. That's what we're doing when we're integrating. We're just taking small little pieces of this and continuously adding them on. And the more we add, we get the area of it, okay? Now, here comes the tricky part. Take this curve and spin it out of the board all the way around. Yes. You've taken this, you're going to take this y equals x squared, we're going to spin it out of the board and spin it all the way around one time so that we've made a what? Kind of like a bowl. What would you say it looks like? A cone, but it's not a flat-sided cone, it's a curved cone. If you think of it, it's kind of like your instruments that you play up there, the end of your, what do you play? The bell end of a trumpet or a tube or something like that, except it goes all the way down to nothing, but it gets big. Does that thing have volume? We should be able to figure out what that volume is. Wouldn't that be fun? All right. So now let's take that. Let's try to build on that. How are we going to find the volume of something like that? Well, let's take it in little bitty pieces. Let's go back to the accumulation function. And I'm going to start with just a small disk. What if we take a small disk out of here and spin it out of the board all the way around? Do you agree that that's going to be a part of it? And essentially, if we can get enough of those and just add them all up, that's the volume of it. Well, what's the volume of this small disk right here? How would we find the volume of that thing? How do you find the volume? What's it going to look like? Anybody got an idea? What's a small little disk here going to look like if we spin it out? It's kind of going to look like a cylinder. It's going to be real tiny, but it's going to look like a cylinder. We're going to spin it out of the board, back into the board. So it's going to have a top that's a circle, a bottom that's a circle, and it's going to be a little bit height there, okay? How do we find the area of the volume of a cylinder? Does anybody remember? We had a generic formula for finding the volume of a cylinder. Or do you remember a generic formula for finding volume in general? Pi r squared h, okay? Pi r squared h. So if we give you a cylinder back in 4th, 5th, 6th grade, wherever we start that stuff, that's how you'd find the area. We want to know what's the radius of it, how tall is it, square the radius, multiply it by h, multiply it by pi, boom, we've got the answer. Well now, what does that translate into if this is our cylinder, this red piece here? Pi is just pi, okay? What's the radius of this cylinder that we're making by spinning this out of the board? What's the radius of it?
No, I'm sorry.
The radius is the height. I think I understand what you're saying, but can you say that so that it's not confusing to us?
Trying to say, like, it's how tall the disk is, like, on the board?
Yeah, that's right. This distance right here is our radius. Okay? That distance is our radius. Okay? So the radius is going to be from the y-axis up to here. That black line becomes our radius. What becomes our height? The width of this thing. So see how confusing this can be? The width is the height and the height is the radius. Okay? So the radius is how tall it is, how tall it is in a flat surface here. The height here, the height is how wide our rectangle is. This should kind of bring back some memories to when we started this back in January, because we got a width a width of it is the same as the height. We've got this tall, and boom, if we can find all those, we just add them all up. Great idea. Problem she found out. Say that again louder. Y'all see what she's saying? The radius, you're talking about on the cylinder or on this, you're talking about on the red box that we've got? Yes, because see, this thing is curving. So this side is a little bit shorter than that side, isn't it? You agree with me? So all we're going to be getting is an approximation. How could we get it a little better approximation? By making the rectangle that's on the board, by making it skinnier. What does that change in our equation here? Pi, r, or h? H. So if we make h smaller and smaller and smaller, then our radius, can we ever get h small enough to where the radius is the same on both sides? No, it's never going to get there, but we can keep getting it smaller and smaller. Does anybody see where this is headed to maybe a little bit? It's kind of like limits, but it's also kind of like where we started. If you go back and look at where we started with area, we said if we make the rectangle sufficiently small enough, keep getting them smaller and smaller and smaller, we'll get down to the right side. And we started relating to that. Instead of the height of it, h, we're going to call the height of it dx. Now, what does dx imply to you that we're going to be doing? We're going to be integrating, okay? So we're going to be integrating. What are we going to be integrating, you think? Well, remember, what's our goal here? Our goal is to get a to get a volume of something. So we've got to keep referring back to this formula here, pi r squared h. Well, our h we've essentially taken care of with dx. Pi is a constant number. So we can put it outside of the integration. So what's left? The radius squared. All right, what's the problem with the radius that you foresee? She kind of hinted at it here. What did Mary say is the problem with the radius on our rectangle that we got here? It curves. The radius is different. The radius is always different. So the radius is not going to be a number. The radius is going to be a function. What do you think the radius is going to be? What function do you think the radius should be here? Remember, the radius is how tall it is from the x-axis up to the curve. From the x-axis up to the curve. From the x-axis up to the curve. That's our radius. What's a formula that tells us how to figure out what that radius is every time? It's just x squared. But how do we find the volume? Is it pi times the radius times the height? So it's pi times the radius squared times the height. Pi times the radius squared times the height. So I hope you can look at this right here and see all of this is it's a more complicated form of the equation of the volume for a cylinder. It's pi, the radius squared, the height. And we're integrating all of that because the radius is a function that's always changing. Well, what else do we need in order to figure out what this is? Pi r squared h. Can you solve this integral right now and get me an answer? That's right. We need limits of integration. What are our limits of integration? Where are we starting and where are we ending, you think? 1 and 0. We're going to start at 0. We're going to end at 1. So we're going to start right here. We're going to go all the way out to the end right here. And this will give us the volume of a shape that's made like that. Okay? Now let's see if we can make that happen on this app. And I apologize, everything has not worked well here. But I have this on here. I don't want cross sections. Square cross. Did I pick cross sections? It's not volume by. It's disk method. Down towards the bottom, you'll see down toward the bottom. You'll see one that says disk method. And let me just kind of walk you through how we're supposed to do this. Okay? You can pull it out over here on disk method. Then I'm going to hit that triangle to make my screen bigger. If you'll hit the little triangle at the top, it'll open up some menus for you. So you can put the function in there. It's x squared. What is my interval? Where am I going from 0 to 1? Horizontal axis of rotation, we're going to leave it at 0 right now. We're going to make that fun stuff happen later on, okay? And then the number of intervals, I'm going to leave it at 30 just for fun there, so it doesn't have to kill itself. So you'll see if you look up here on mine, and then you can maybe make yours look like that, I've got the picture kind of like the flat picture on the board. But if you look down here in the black area, that's got it rotating around something there. Go down to integral calculus and scroll disk method. Integral calculus disk method. So can everybody make their iPad make that funny looking shape? And you can move it all around so you can see this is what it looks like on the inside and the outside.
Wait, how come yours is finer than mine?
Okay. Okay, your function is x squared. Oh, your axis, your horizontal axis of rotation should be 0. So just tap that and make it 0.
There we go.
That's right. And now you can see there's also a place to put number of horizontal axis, number of intervals. I just left it at 30. If you make it 200, you'll make it smoke a little bit, but it'll get to be a finer shape there. But suddenly, now you can get a visual picture of what that looks like. I think that helps students sometimes, that they can get a visual picture. Okay, now what are we doing? We're doing x squared, and we're talking about integrating from 0 to 1. So let's do this. If you'll go hit that triangle right there. Now, your function has got x squared. Your interval is 0 to 1. All right. Then the next one down says the axis of rotation. What are we rotating this thing around? The x-axis. So you want it to be axis of rotation to be 0. Probably just have to hit it and you have to tap on it first. And then 0. And then the number of intervals, it doesn't really matter. It's just going to give you an estimation of. I did 30 to have it there. So suddenly, now you've got a picture down there that you can see what it's going to be like, okay? The number of intervals, think of it as the number of rectangles. I did 30 just so you could see it, but I think he's got, looks like 5 or 6 done here, and that's great because then you can really see that it's rectangles there. The more rectangles, the more accurate you're going to get. Yeah, 100, 200. The more accurate you're going to get with that, the more rectangles you put in there. Okay? So I would just want you to be able to visualize this because it obviously is hard to draw on the board, and Jasmine's going to go crazy trying to watch the video saying, what are they doing right now? But anyway, she'll have to figure that out some other time. We'll talk with her on that. But now you've got a visual of what it looks like, okay? Because it's going to get more challenging as we do other things with it here, okay? Would the integration of this thing be very hard? No. What are we going to be doing? To actually figure it out, the volume is going to be pi integral 0 to 1 of x to the 4th dx, because x squared squared. Well, that integrates to become x to the 5 over 5th, x to the 5th over 5, excuse me. Evaluate that at 1 and 0. So 1/5 pi is your answer. And I think if you'll look on your app, if you pull the window down, oh, it tells you down there that your volume, mine says the volume is approximately 0.627, which 1/5 of 3.14 is about that number there. Okay? Questions, comments, observations? Yes, sir. I don't know, to be very honest with you. Side note, since you said that, has anybody seen they can 3D print a house in 4 hours?
What?
I'll have to send you the video.
Okay, now when they actually print it, like what?
It's ingenious. This has nothing to do with this, but it's ingenious. All it is they've got a machine set up, and it's not a square house. It's kind of a circular house. The machine, all it's doing is it's pouring concrete. It runs around and it pours a slice of concrete all the way around, comes up, it comes back, and it pours it again. They can build it in 4 hours.
So it's an
actual house. Cost about 10 grand to do.
What?
So now think about that.
Oh my God.
Think about that. Think about what that suddenly does in third world countries.
What that does for people who want to move out.
Yeah, think about, yes. So I mean, but that's so they can actually 3D print the house. It was running on its own there, and there was a guy to put in something every now and then. You know, if you wanted a box for something, and you know you want a window in the house or something. It was absolutely amazing when I saw it. Okay, so do you get a visual of what this looks like now? Do you see how this type of thing could be very beneficial to industry? Look at the water bottle sitting close to you. How do they figure out how much it will hold? Obviously, yes, they could fill it up, measure the amount of water in there. But just take, is this going to spill if I do this? Okay. If I take this, and if I look at the profile of this as my curve, all I've done is I've taken that curve and I've rotated it around the x-axis. So suddenly, if I can figure out what this shape is here, if I can write a function for it, I've got my volume for it. Think about the old-time Coca-Cola bottles. Do y'all know what the ones I'm talking about that are, let's pull up a picture of that if we can find it here.
This would be a horizontal line, would it not?
Yes. Yes, if I do it that way, we're rotating it around a horizontal line. Old Coke bottle. Think about these images here, these strangely shaped bottles that they might get. But if you imagine laying this on its side, if I can figure out what the outside shape of this is, suddenly I can figure out what volume it will hold there, okay? All right, so let's go back and let's look at the next problem that we have there, okay? So before we go further, how would you summarize, if you've got to write a formula for finding the volume, what's the formula for finding the volume now? Pi. Some function, okay, I'm going to call it R for radius, some function squared dx. Boom. That's our basic function right there. Now we're going to get into all other kind of funny things here over the next 2 to 3 days, but that's our base function for everything we're going to be doing there. Pi, some function squared, and we're going to integrate from somewhere to somewhere. Remember, we're dx, so my function has to be x, my limits of integration, all of that has to be x numbers. Well, let's look at something funny like this. Now, don't get discouraged or don't get distracted by all the pictures I've got up here or by all the pictures you've got. Focus on the question at hand to begin with, okay? Determine the volume of the solid obtained by rotating the region bounded by blah from x equals 1 to 4 about the x-axis. Okay? So this first picture here that's got the curve in red and the green shaded in, that's our flat picture of this. So we're going to take that and rotate it around. So why don't you on your app now see if you can get that picture to show up there. Go up to your function and change your function to that. Oh, I just have to add on to it is all I have to do. If I can add on to it. How do I add on to it? Oh, I can't add on to it. See, I'm not smart enough to work this thing.
How in the world do you just...
I want x. But how do you get a plus sign after the x squared? Anybody figured that out?
Yeah, you click on whatever it is and you just hit plus. I don't know how to do... Oh, plus. Yeah, that's what oh, that's mine. Plus. There we go. Oh, but it's...
I don't want to edit anything.
Well, it'd be great if they just... Oh, there.
How'd you get the minus sign there? I'm not smart enough to do that.
Thought I just.
Oh, now it'll do.
Yep.
Okay. See, I wasn't smart enough to do that, I tell you. Minus, can you just do 4x? Nope. 4 times x. I did the times x and then it changed it to 4x there, okay? And then we...
Yeah, I got the parentheses. How do you do plus?
Huh? I was coming back to ask. Yeah, every time I hit the plus, I get that out there. So, I don't know how to get the plus 5 after it. Anybody got a solution?
Yeah.
All right, but then we need a minus 5 in there. So, okay, here's what he did is, yeah, but not the way he had his written there. Make it a plus 5 out there, please. How do I do a plus 5? You don't know either?
No.
Jeez.
Oh, yeah. Oh.
You see what I'm saying? I'm trying to get a plus 5 out there, and I don't know how to do that. I sure am glad I'm not watching this video online, wondering what they're doing. You got to be frustrated right now. I'm sorry, Jasmine. That's right. The field. Just remember, you're having fun while we're sitting here stuffing through all of this here. That's right. It's the basic math. Plus.
No, even better. It's copying and
yeah.
just trying.
Can anybody get a plus 5 after the minus 4x? Oh, that's not a good answer.
I don't know what it changes.
It changes something there. Okay.
Oh, yeah. It does. It flips it around.
Plus 5. I got everything highlighted, and then I was able to do the plus 5. It's out of order, but it's there. What I did is I closed it out and opened it back up, got everything highlighted, and then did plus 5 there. Oh, and then I changed it.
Wait, how? Oh, my God.
Yeah, plus 5. Okay. Woo! Yep, highlight everything, and then you can do plus 5. What I had to do was I had to hit the X up at the top, and then go back in, and it was suddenly highlighted there.
So once you highlight, what do you do?
Then do plus 5. Yeah. Now you can go back and get rid of the plus 5 in there, maybe. All right, so what's our interval going to be for this one? 1 to 4, okay? So now, and the horizontal axis and number I'm going to leave to be the same. So, you see that on your screen you should see something very similar to the flat surface that we were able to see. And if you'll go down to the black area, you'll see what that figure looks like in 3D. So it's, you know, it's kind of like, I keep going back to musical instruments, but it's kind of like the end, the bell, I think you said it was, the end of a trumpet or the end of a tuba or the end of some type of wind instrument. But it's it gets small and then it gets larger. But you can see that there's definitely volume to that thing there. So, if you set it up, look, yeah, you could almost see it as a table here. If you turned it up on the small end, or a cornucopia is what you're thinking of, I think. You could think of it like that, but you've definitely got a figure here. Now, that's what these other figures on the board are trying to represent. If you were to rotate it around, you'd have something that looks kind of like this one on the right side here. But we need to find the volume of it, okay? So what's my integral going to look like to integrate here? I'm going to be integrating dx. I know it's got a pi. What's going to be my radius? The formula, the x squared minus 4x plus 5. And what are going to be my limits of integration? What would be my limits of integration here? 1 to 4. Okay? Now, this becomes more challenging to integrate because I've got x squared minus 4x plus 5. Yes, it is 1 to 4. Thank you. Would you agree that this becomes a little more challenging to integrate? Because now I've got to square a trinomial. Anybody remember how to square a trinomial? It's not FOIL. It's not SOAP is how you factor a difference or sum of cubes. Squaring a trinomial, you're going to get 9 terms. I used to teach it as you'd line them up, kind of like long multiplication, and multiply the 5 by everything, the 4x by everything, the x squared, and then add like terms. It's confusing. It's complicated. We are not testing your skills to do that. So this is where having a calculating device that will integrate, like my trusty device here will, comes in extremely handy. And I'm going to give you some formulas that would probably be wise for you to put in here, okay? Remember we talked about y1 minus y2 and y2 minus y1 on the last test? It's real important that you're able to do that here. Here's what I would recommend that you do for this, okay? I'm going to put my function in y1. So I'm going to put in x squared minus 4x plus 5 in as y1. I'm going to leave y2 blank. That's going to be for some other fun later on, okay? And now I'm going to put this in so that it will always be there for me. Y variable in y3, I'm going to put y1 no, I'm just going to put y1 squared is what I'm going to do. I'm going to go back and do that again. Variables, y variables, I'm going to put y1 squared. Now, I'm going to keep that. By the time we get to next week, you're going to have a y3, a y4, a y5, and y6 that you always want to keep there probably, maybe a couple more. So now we're wanting to integrate this thing. Which one are we wanting to integrate, y1 or y3? y3, because we're wanting to integrate something squared. So I'm going to go to my calculator. I'm going to say second, calculate. I'm going to integrate number 7. It's going to graph both of these pictures on here. Understand that when you are integrating this y3, it's going to look nothing like this 3D cone that we got, okay? We're not integrating y1 like the board says, so we're going to move down to y3. Are we starting at 0? Nope, we're going to start at 1. We're going to go to 4. That shape looks nothing like what you expect the volume to. Your calculator can't do what your iPad did and made it look like a shape of volume there. But that's the number part of integrating that function from 1 to 4, 15.6. So now my answer for this is 15.6 pi. Hopefully I did that right. That just seems way easy, doesn't it? 7, we're integrating y3 from 1 to 4. We got 15.6 again. So I would write down my answer as 15.6 pi. You know, obviously, if you could multiply it by the pi and get something different than that. Is that complicated? You must be able to use your calculator on these, okay? Got to be able to use your calculator on these. All right, let's see if there's anything else interesting here to look at. All right, find the volume of the solid formed by revolving the region bounded by the graph of blah and the x-axis, about the x-axis. Notice we don't give you any limits of integration this time, do we? If you've got the picture, you can probably determine your limits of integration. But if we don't, if all I give you is this and the fact that it goes around the x-axis, how can you find the limits of integration? Set it equal to 0. When is the square root of sine x equal to 0? Now you've got the picture here so you can see that it's 0 and pi. But we can find our limits of integration by setting this thing equal to 0. So, what's going to be my integral for this? Somebody. Pi. Somebody else. Jordan told us the easy part. Square root of sine x squared. All right. Jared's in. Somebody else? 0 to pi, pi to 0. All right. Somebody else? Anything else? Dx. Boom. You integrate that, and you're going to get whatever the volume of this is down here. If you want to try that on your, obviously you can do that integration on your calculator. You can see that image on your iPad. I encourage you to take the time to see some of these images on your iPad because it's going to get you a better understanding of it if you can see visually. Do you see, can you visualize that this kind of looks like a football? Because it's kind of egg-shaped, and we're going to have an area out of it. That's one you could probably integrate. You could find out, you could do that without the calculator even probably, but you should be able to do it and get, I think, 2 pi out of the answer here. Yeah, I think that's what you're going to get out of it. Do you ever expect to get negative answers? No. Why not? We're area, we're volume. So you've got to have a positive answer out of these problems here. Okay? Is this complicated yet? 2, and then multiply by the pi out front, and you get the 2 pi, okay? Common thing students would do is leave the pi off out front. Anytime you're rotating something around the x-axis, you're going to wind up with a pi in it there, okay? Now notice, because you'll see this on your homework, you see where it's got this little blue thing circling around the x-axis? That's telling you that we're going to be rotating it around that particular line, okay? Which, if you're really thinking, makes you think, wait a minute, later on that thing's going to be changed to somewhere other than x. And yes, it is, and we're going to suffer through that together here. It's lots of fun. All right. Let's set up a couple of integrals here. I don't know what that one is. Yep. Let's set up just, what do we got, 3 more of them? Let's set up a couple of these to be sure you've got an understanding of it, okay? Y equals negative x plus 1. There's the picture. Set up what the integral is. Do not integrate it, but set it up. While you're doing that, I have a lovely AP bulletin to give you. I can check the box that says I have given this to you. Your AP teachers have probably told you this in the past, but it is important for you to have, wow, that's interesting. It's important for you to have a general understanding of what you're agreeing to when you take the AP test, okay? For example, are you aware of the fact that you're not supposed to discuss with anyone anything on the test for at least 48 hours? That anyone includes me. So you're not supposed to discuss it with anyone. You can have, and I think this will lay out in, you can have 2 calculators in the test. You cannot have 1 calculator and spare batteries. You can have 2 calculators, but not any spare batteries. Yes, and everybody says, why not? Well, I bet if Matthew was sitting up in front of me, my calculator could die and my batteries could roll up beside him so that I had to go get them and see what he was writing on his paper. That's my speculation on what that is. So, anyway, that's what I would recommend. Just read over it so you're somewhat comfortable and somewhat understand what's going on. We've never had any issues, but just so you understand, AP takes this stuff seriously. If I know of schools that have had an issue and they are never allowed again to give an AP exam on their campus. They can teach the course, but the students can't take the exam there. They have to go somewhere else. So don't mess it up for us. All right, so back to calculus here for a second. We're integrating. We're going to have dx. We're going to have pi. And let me just tell you, This has been an FRQ on the AP exam for the last 8 years. It's important for you to get points out of this. Right now you're sitting here, man, this is easy. How can anybody miss it? When we add in tomorrow and when we add in next Tuesday, that's when your head starts hurting, okay? So it's important that you get points out of this wherever you can. Be sure that you give the pi. Be sure that you give the dx. If you can do nothing more than give me pi dx and the limits of integration, you probably got 2 points out of just that part there. So be sure you can get in the habit of giving at least that much information here. Yes. 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 You've got, normally you're getting 1 point for pi and you're getting 1 point for the limits of integration there. That's what it's been the past few years. So, what are my limits of integration? 0 to 1. How do I know that? Because I'm integrating this black line and it starts at x equals 0 and it intersects the x-axis at x equals 1. So we're going 0 to 1. The problem said we're revolving the region around the x-axis. So what is my integrand? It's going to be something squared. What is it? Negative x plus 1. Okay? All right. I feel like y'all have a very good understanding of this, very good feeling. Do y'all feel like that? I think you do too. Okay? So I'm going to look at these, see if there's anything special out of any of them. I don't see anything any more special there. So I'm going to stop talking. You can work on homework. You can work on FRQs. You don't have a web assignment to work on, so you just got homework and FRQs you can work on. Thank you very much.